Questions about that? So I'm going to get to the 3D case now, which is the reason why I dragged you through all of this. One very nice property that I want to point out here, because it's harder to visualize in 3 dimensions, is that I've used this parameter theta. If I change theta by some small amount, say I change by 1/10 of a radian or something, then the amount of rotation changes by a small amount, right? The rigid body will move by a small amount, and it doesn't matter if I change by, let's say, if I go from 0 to 0.1 or if I go from 1 to 1.1, a change of 0.1 corresponds to the same amount of change for the rigid body. In 3 dimensions for 3D rotation, it's very, very hard to get that property back until you know how to do it. But if you were just to design something yourself that has that property, so if I vary my parameters of rotation by a little bit, how do I make the variation in 3D rotation be the same amount of little bit? And this is going to be very important if you do something like, say, design a filtering and tracking method, because you want to measure the errors in your tracking and you want to do that in a consistent way. Otherwise you'll get confused. You'll think you have huge errors over in this part of the rotation space and very tiny errors over in this other part, when in fact the errors might be the same in terms of how much the body is actually rotating. So that's the kind of difficulties we get into. In 2D it's very easy to see these things. It gets harder in 3D. Questions about this? So I'm going to go to the 3D case. Okay, so now we go to try 3D rotations. I don't think I feel like writing 3 by 3 matrices with a bunch of m's and subscripts and all of that, so I'll just write it with dots inside. So we have bigger matrices now. I'll just write some dots here, make it fast. You can fill in the m's if you like. So now I have 9 degrees of freedom for a 3 by 3 linear transformation with real valued entries here. So we start off with 9 dots, and I want to use the same kind of reasoning now. Let's give names to these column vectors here. So I will call this V1, V2, and V3. So I'll use that to refer to these columns. Because if you remember in the 2D case, we kept referring to the columns. So I will just refer to those as V1, V2, V3. I may also want to refer them as Vx, Vy, and Vz, but I've got to be careful because I don't want to make them look like scalar subscripts. So just say V1, V2, V3. All right, so constraint number 1. What was constraint number 1? Anybody remember? Let's see. Yeah, so the lengths of the vector should be 1. Right? So if I square each of the components and add them up, I should get equal to 1. I guess I can just write that using norm notation from linear algebra, but if you don't remember that anymore, just square each element, add them up. So the norm of V1 should be equal to the norm of V2, should be equal to the norm of V3, should be equal to 1. And so we started off with 9 dots. How many did I just lose? 3, right? So I lost 3 there. So I have this, so this thing gives me a degree of freedom penalty of 3, right? So I lost 3 degrees of freedom. All right. 2 was this thing about inner products, right? You have to avoid shearing, so you have to have the inner products be equal to 0, right? The dot products between the columns. Which columns do I pick? What's that? All of them. Let's see. Well, dot products, there's not really a triple way product here, right? So we got to do it in pairs. Very good. So we do all pairs from combinatorics. Let's see. 3 choose 2 is equal to 3. So there's 3 pairs. It doesn't matter what the ordering is because dot products don't care about ordering. Cross products do. So I guess I just need to pick the pairs here. So I say, okay, I need to have V1 dot V2 equals 0. I need to have V2 dot V3 equals 0, and V1 V3, right? Get the other pair. So I need to have V1 dot V3 equals 0. So when I put all of that together, I guess I've lost 3 more degrees of freedom. Hey, not bad. It's doing the same kind of pattern as for 2D. So we lost 3 more with these. We still have the third condition, which is we do not want mirror images. So 3, we need to have the determinant of this big 3 by 3 matrix be equal to 1. And again, this is not going to drop the degrees of freedom. This is going to keep it the same. It's just going to eliminate half of the cases. In fact, because every mirrored transformation has a corresponding one that's unmirrored, it's getting rid of exactly half of them. So in the 2D case, as I said, there was like a good circle and a mirrored circle. There was the true rotation circle and the mirrored circle. We now have remaining some 3-dimensional set or 3-dimensional space of rotations. We have 3 degrees of freedom. We have to get our fingers on it somehow, describe it in some good way. We have 3 degrees of freedom left, and it was in 2 different components. There's like the mirrored part and the unmirrored part. This constraint eliminates the unmirrored part. So if you want to have the mirrored part, then just make the determinant be -1. All right, so we're going to avoid that. So by the time we're done, we finally have, which we should have, we get all the way down here past these constraints and we have 3 DOFs for 3D rotations. All right, so I'm going to start off with a simple way to describe 3D rotations, and then after that get to the more let's say appropriate way for doing the things that we want to do. So to start off here, and we'll take a break shortly, let me just start off here with the 3 canonical rotations, which are yaw, pitch, and roll. So these are going to be 3 independent parameters we can use to describe rotations. They're the most, I would say, intuitive and easy for people to understand, but they cause a lot of trouble and damage later. So I'm going to first introduce them. We can talk about them. They're helpful if you keep them separated, but when you combine them together, you sometimes end up with a mess. First of all, just make sure we all know what we're talking about. So yaw is going to be this, right? Let's all do this together. So yaw is like this, right? Good. Then pitch, so yaw is like no, right? And pitch is like yes. And then roll is like this, which if I understand head gestures around here means maybe, right? So I'm not sure. Is that right? So we have yes, no, and maybe. So let's all do this together. So yaw, say it together. Yaw, pitch, and roll. Roll, right? So keep those straight. It's very, very helpful. Yaw, pitch, and roll. So let me just write out the matrices for these, and then we'll break. Yaw, I'll write it like this. I'll say it's a rotation matrix with a parameter alpha, and it looks like this. Cosine alpha 0, sine alpha 0, 1, 0, minus sine alpha 0, cosine alpha. This looks a lot like the 2-dimensional rotation matrix if you look at the corners, and the center part looks a lot like the identity matrix, right? So the center part looks like the identity matrix because it's basically saying don't disturb the y coordinate. If I do a yaw back and forth, notice that the notice that the y coordinate is not changing, right? Y is up. I forgot my coordinates for a bit here. Yeah, y is upward. So notice y is not changing when I do this, correct? Only x and z are. So it's essentially a rotation in the xz plane. That's why it looks like the 2D rotation matrix. There's a little bit of change with respect to it, but that's because these are appearing in the corner. If you do a circular shift downward and over, then it'll look exactly like the 2D rotation matrix being applied. So pitch is very similar. We write r of beta, let's say. Which axis is left undisturbed for pitch? So do this, x is undisturbed. So we can already guess that the x part is going to look like an identity matrix. And then here in this remaining part, this remaining block, we just make the 2 by 2 rotation matrix, but with a beta in it. Cosine beta minus sine beta, cosine beta. And then finally, roll roll should leave the z coordinate alone then, right? So z is going back and forth, z is the depth. So z goes back and forth. When I do a roll, I should not be interfering with that. We did alpha, beta, gamma. So we'll make gamma the parameter for that. We get cosine gamma minus sine gamma, sine gamma, cosine gamma. So the upper block is exactly this two-dimensional rotation matrix, but corresponding to the xy plane, and then the z part is the identity 0, 0, 1, 0, 0, 1. Right, so that's what we get. And now if you want to generate any other 3D rotation, you just need to pick some amount of yaw, some amount of pitch, and some amount of roll, and then you can apply them sequentially. And that will generate any rotation, but it might not provide, and it in fact does not provide, a beautiful representation in the sense that I mentioned, where a small change in these parameters may or may not correspond to the same amount of change in actual physical rotation. And that's the difficulties we'll be getting to after the break.